Hello dear students, welcome you all. So in this lecture I am going to discuss about the applications of thermodynamics to thermoelectric effects, right? Application of thermodynamics to thermoelectric effects, right? So here we are going to apply the different laws, different equations of thermodynamics to study the thermoelectric effects. In fact, we have different types of thermoelectric effects. So we have already gone through the thermodynamics, right? Now what is thermoelectric effect, right? So you can see from here that thermoelectric, this word is made up of two words. Thermo means temperature, right? And electric means electricity, right? So thermoelectric effect is basically, the conversion of temperature difference into electricity and conversion of electricity into a temperature difference. You can say like that, right? Or I can say when temperature difference is produced across the junctions of a thermocouple, then there is a production of EMF in that circuit. Conversely, if I pass electric current through a thermocouple, then there is always production of a temperature difference at the two junctions of the thermocouple. So this is thermoelectric effect, right? These thermoelectric effects were first studied by Thomas Seebeck, right? Thomas Seebeck, who was a German physicist, right, in 1821. So, the effect that Thomas Seebeck studied is also known as a Seebeck effect, right? Beside to it, we have one more thermoelectric effect, that is Peltier effect. Peltier effect, right? It was studied by Jean C. Peltier in 1834, right? We will also study Thomson effect at the end of this entire topic. So in this topic we are going to discuss about the Seebeck effect, Peltier effect, and then Thomson effect, right? So these are the three topics that are covered in the application of thermodynamics to thermoelectric effects, right? So I'm start with the Seebeck effect, right? So Seebeck effect, right? So before going into the discussion of Seebeck effect, first of all we will understand what is a thermocouple, right? What is a thermocouple? Thermocouple is basically a combination of two different metals. If we have two different metals and if I join these two metals at their ends, then this entire arrangement is called thermocouple. And the two ends where these two metals have been joined, they are called as junctions, right? So to understand it, let's consider we have copper and bismuth. Let this is copper and let this is bismuth. These are two different metals that I have. Now what I am going to do, I am going to join the ends of these two metals. This is copper and this is bismuth. So if I join the ends of these two metals, now this entire arrangement is called thermocouple, right? This entire arrangement is called thermocouple. Now the two ends, right, where these has been joined, obviously I have joined here these two and here at these two. So these are called junctions, right? Uh, Initially here in this image, in this picture, I have taken a wire to join these two ends, but in reality these two ends are joined with each other in this way, right? They are attached with each other, right? So these two ends where these two metals are joined, they are called junctions, right? So we can have different junctions due to the combination of different metals. Now when if we look at the thermocouple, when I have joined copper with bismuth, there is very important thing that is going to happen. We know very well that in all the metals there is different density of free electrons. Clear? Free electron density is different, right? Different metals have different Fermi level, right? We have learned about it in statistical and thermal physics also. Different metals have different free electron concentration, that is I'm writing here density of free electrons. So when I join one metal with other, suppose for example copper has high density, right? It means copper has more free electrons, right? I can show them here. Copper has more free electron. Now these are the arrows are the electrons. Clear? They are in fact randomly oriented. They are moving randomly inside the copper wire. They are not moving in a particular direction when there is no external field applied, right? So in this way, right? This is the case of copper, right? Now let's take the case of bismuth. So in bismuth, the concentration of free electron is less as compared to copper we are considering here. So let in this case it is like that, right? So when I join these two metals together at these ends, what is going to happen? It is obvious that the electron will start flowing from the metal having high electron density to the metal having low electron density, right? Because this is the tendency of the different metals, electrons. So what will be the result? The result will be the flow of electron will continue from this metal to this metal. A one stage is reached when this metal copper will acquire positive charge at this end due to the loss of electron, and this will acquire negative charge due to the gain of electron. The same thing is going to happen here, right? Now due to this drift of electrons from one metal to other, as I show you here that these two different metals attain positive and negative charges at their ends. So now the further flow of electron will stop, right? And a kind of potential is set up at these two junctions here and here. Clear? So obviously these two junctions will have some potential due to the movement of electrons. So this potential difference is called the EMF or potential set up at these two junctions. I can say EMF or potential difference set up at these two junctions, right? Now we know very well that the density of the free electrons or the Fermi level of metals depend upon temperature. Clear? So I can increase or decrease the density of free electron by changing the temperature. So if I make this junction cold and this junction hot, what bit will be the result? The result will, the junction which will become hot, it will increase the movement of electrons from one metal to other, because electron will become more mobile, more electron will be available in the conduction bands, and they will start moving fastly. But at the cold junction, the things will get reverse, right? The movement of the electron will be very low. It means now the potential difference at these two junctions will increase, and we will have a resultant current flowing in this entire thermocouple. So this is the Seebeck effect, right? This effect, Seebeck effect, is nothing but it is this entire result, right? This was studied by Thomas Seebeck, right? So this is about the production of electric current in a thermocouple when the two ends of the thermocouple are kept at different temperatures, right? And then there is always a flow of current inside this thermocouple, right? I can show you the actual diagram that was used by Seebeck. I can draw that diagram. Sorry. Right. So the upper metal is copper and the lower metal is bismuth, right? Now I have taken two beakers, right? Right. So now I have placed water here. This is water or some other liquid you can say, and what I'm doing, I'm making it hot by applying the heat from this side. I'm heating it now with the application with the use of a burner. So it is hot H, and here I have placed some ice cubes. It is cold. Right. This is cold. Right. This is bismuth, and this is copper. Right. I have placed a galvanometer here to detect the movement of any charge or I can say current in this circuit. This is a galvanometer, right? Now when I will now you can see this is copper, this is bismuth. As I explained here, this constitute a thermocouple, right? Now this is a thermocouple, right? right? And this is one junction, and this is other junction. So you can see here that one junction is hot and other junction is cold. So as I explained you here, what is the reason for the production of EMF in this entire circuit or flow of current in this entire circuit? It is because of the difference in the density of free electrons, right, in these two different metals, and this density of electron depend upon the temperature, right? So by increasing temperature at one junction and decreasing temperature at another junction, I can change this density of electrons and I can induce a potential difference across these two junctions. So obviously there will be a flow of current. So when this particular type of junction is made, then in this case the current flow in this direction, because it is very important to remember the flow of electric current in this junction, right? Galvanometer will detect the flow of current in this junction, right? So this is about the Seebeck effect, right? Right. So you can see here now Seebeck effect. Now, what will be the direction of the electric current? How we have to remember it? So it is very simple. In this case, you can remember it by this trick: cubic. Cubic stands for copper to bismuth at a cold junction. So you can see here it is copper to bismuth at a cold junction, and here the things is reverse, right? It is from bismuth to copper at a hot junction. But if I have to remember this flow of current direction, then cubic, right? If I have different metals, obviously the flow of current will be different. It depends upon the actually density of the electrons and all other properties of the metals and temperature difference as well, right? So this is about the Seebeck effect, right? Now I'm going to write a very important result of Thomas Seebeck study. What Thomas Seebeck did, he studied the thermocouples of the different metals, right? And thermoelectric effect, Seebeck effect produced by the combination of different metals. And then after he arranged these metals in this series, right? This is called Seebeck series. Seebeck series. I'm writing Seebeck series here. You can see bismuth, nickel, cobalt, platinum, copper, manganese, mercury, lead, tin, chromium, silver, not gold, then silver, then zinc, then tungsten, then cadmium, then iron, and then arsenic, and then antimony, right? So this is called a Seebeck series. Clear? You can see here it starts from bismuth and end at the antimony, right? Now the important property of this series is that if I made a thermocouple out of these different metals arranged in a particular series, the produced EMF will depend upon the difference, the separation between the two metals. For example, if I made a thermocouple of these two metals, then the EMF will be less for the given temperature difference. But if I made a thermocouple of these two metals, right, then in that case the produced thermo EMF will be more for the given temperature difference. difference, because the produced thermo EMF depend upon the separation between the different metals in this series. One important feature of this series is that when you made a thermocouple of this series in this order, right, in that case, the flow of electric current at hot junction will be in such a way that it will go from the metal that comes earlier to that metal that comes later. So, if for example, I took the case of bismuth and SV antimony, right? Then what will be the direction at the hot junction? It will be bismuth to this. Yeah, that is what I am saying. At hot junction, it goes from this to this, right? Similarly, if we make a thermocouple of copper, where is copper? Copper and iron. Clear? So obviously, it will be from copper to iron, because copper comes earlier than iron in this series, and the direction of the flow of current at hot junction will be from copper to iron. So we can remember it as hot coffee, right? I can take the example of this copper to bismuth. So bismuth comes earlier, right? Bismuth, and here it is a copper. So obviously at hot junction, from bismuth to copper, so it is already there, right? So this is the importance of this Seebeck series, right? It is directly linked with the direction of the flow of current, and also with the magnitude of induced EMF in the thermocouple, right? So this is about this. Now the amount of EMF induced in this circuit, that depend upon the temperature difference in across the two junctions, right? So the amount of EMF produced here, I can write the expression for that. EMF is equal to minus S delta T. This is the result that has been derived by Seebeck. EMF is equal to minus S delta T. Here S stands for Seebeck coefficient, and delta T is the temperature difference, or I can say temperature gradient. Clear? Across the junctions, across two metals, right? So this is all about this first type of thermoelectric effect, right? It was a Seebeck effect, right? So this is all about it. Thank you very much.